Want to get going here. So we don't have that many people this time around. Right now, at least 14. They'll probably show up as I start talking. What did we talk about last time? Well, we've been going over a lot of your projects. I'm really excited to see how far or where you get when it came to your projects. And I have to remind you, some of the projects you do not have to use Vegalite. And so I think we have this nice, maybe you don't think it's nice, spraying or splaying, that's the term, not spraying, splaying or divergence in the technologies we're going to be using. I could say, hey, everybody needs to use Vegalite, but if half the people are using maps, Tableau is better for maps, and things like My Maps is better for maps. If you have a combination of maps and visualizations, maybe Tableau is better. If anyone's an expert on Tableau, I know the COVID testing group would love to hear from you because we're trying to figure out how to make sure that you have global access for your Tableau account. And I'm not sure if it's a matter of, I would have to look into it a bit deeper. Um, not sure if it's a matter of how it's set up or it has to be a particular account. So I know there was globally accessible from for another group last term, the grad students group. I thought they were just using the accounts that I gave them, but they also happen to be Tableau experts. So I can also reach out to them. But if anyone knows off the top of your head, that would be very useful to help us make sure that you have globally visible Tableau accounts if you're doing a Tableau version of the project. Um, Originally, I wanted more coding. If it was a computer science program, I'd be like, yeah, it has to be coded. But not everyone's programmers, and you guys, you're going to hate me enough for programming for 1400 and 2400. I figured I didn't need that extra little level of hate afterwards. If you're doing D3 though, there's some, I know I had a group do D3 last term, and I think this term we have a combination like leaflet and D3 in one for the local people skating, skateboarding, that sort of thing. Sorry, I'm trying to remember how you guys wanted to call your group, but local outdoor activities. That's fantastic. If you want to code that up, I'm all for it. If you want to code, I'm like it. There's an overhead to it, but it's something that you can get something really, really impressive if you're coding it. So the D3 group last term was looking at um, extraplanet, exoplanets, exoplanets, planets outside of our solar system that they've detected. So they got a whole lot of NASA data, and they put it in D3, and they had animated transitions. They had all this kind of stuff going on. It was beautiful to behold. It's hard to do, so I'm not going to ask people to do that. Oh, nice. Nice. You got it solved. You got the Tableau thing sorted out. So you guys are going to be the experts in Tableau. So if other people want to publish their Tableau stuff, I'm going to be pointing them to you. Very nice. Thank you for letting me know. So last time when we were looking at this, just that's the project. Last time we were looking at this, we were looking at graphs. The reason we're looking at graphs is because computer scientists and a lot of other communities are sort of blinded with these sorts of things. We love these things. If you have something that you have to show the connections between things, graph. LinkedIn is a graph. That's actually the link in LinkedIn is a graph. Facebook graph. If you're talking about, and it comes up in all sorts of places. All large chunk of the uh, digital linguistics or the computational linguistics groups. A lot of the people that are doing any kind of uh, text analytics for Shakespeare or some or English literature. Graphs. Who's who are they connected to? How is the wording connected to other wording, and what's the correlation between these things? Visually representing the analytics that you're doing in a lot of the social sciences pops up graph form because all you're looking for, what you want, the essence of it is just what's connected to what and how much it's connected. And this dates all the way back to the Seven Bridges problem, which is this beautiful abstraction from something what looks really complicated. And you just go, screw it. I don't care what this looks like up here. I don't care what this island looks like. I don't care anything about any of the geography. I just care that the person has to traverse seven bridges and go back to the start. Can I do it? And so Euler's approach is abstract away everything else other than The graph, the connections between different places. That's what you use a graph for. Now, there's a couple of things you can do with a graph, and we'll get to those in a second. So we have a directed graph, as in it goes one way or both ways, but there's a directionality to it. Fine. This undirected, as in if it's not directed, it goes both ways. Like a road, by definition, you'd say undirected, but in fact, a road is, I have an arrow this way and an arrow this way for each of the different sides of the road, going each direction, because there's some places that have a one-way street. If I'm looking at traffic and the ability to traverse the city using a GPS, it's a directed graph. And weighted, as in how long is that street between the intersections? That would be part of a directed weighted graph. I have an unconnected graph, so if I can't get to this place, unconnected graph would be the bike paths in most cities. There's always some place where you have to drive on the main road. So you have the bike path, and then you have to pick up your bike, cross an intersection, and then go back on the bike path. It's unconnected. We have the degrees. So how most intersections are 4. They have degree 4, as in it has 4 different lanes going into that intersection. That would be typical. If it's a 3-way, like one of those T crossings, it's a 3. The node, the intersection, if that's the intersection's the node, is a 3-way intersection. For a lot of graphs, like how many people I have, how many friends I have in LinkedIn, if I have 500 connections on LinkedIn, your degree is 500 or more. Okay. Cycle is, I know you, you know this other person, that other person knows me. It forms any form of cycle, not just 2, but 3 or more that goes in a circle. That's useful to know just in case you need an alternate path. So if let's say I have a network, a computer network, and this, someone cuts the wire here, or this computer goes down, how do I reroute my network? If I only have one connection, I'm screwed. That's what happens when your ISP goes, like your connection to your ISP, internet service provider, goes down, right? You have no other connections, you lose your internet. The internet cannot have that. So if one of these major hubs goes down, they need to reroute. That's what a cycle is. You want to be able to find out what the cycle is. And if it's acyclic, you don't have any problems with going in circles. Okay. An acyclic graph, a connected acyclic graph is a tree, as in it's the mathematical definition of tree. But this is what we look at from computer science standpoint. What I think I gave, I'm giving in 2400 as a regular assignment. A tree is a rooted tree, as in I have a starting point, some root node, the start, the C colon drive on your computer, and then it goes to this one and this one. It goes to other, it's going to subfolders or other nodes, but it can't go, it never goes back. It never cycles around. It's acyclic and it's directional. When we look at, by the way, if we look at, when we look at object-oriented programming for 2400, you'll see it again. It is what objects are. We get hierarchies. So we had a base class, and then that has subclasses which have subclasses. And we can figure out the depth of our tree. So one of the weird things we have is we need to worry about how this thing is laid out, because in fact, you can represent it the same tree multiple different ways, put it in different positions, and it's the same data. And so the reason why this is so studied is, well, you're choosing how to lay this thing out. There's no default way to lay this thing out. There's no default way to draw an edge. There's no default one way to draw a node. It's all sort of up to the designer, and therefore that's where the fun stuff is, right? That's where we need to know our perceptual principles, why things work the way they do. So oftentimes we'll topologically lay it out. We're trying to show structure in the tree based on how it's laid out. So if we have a group of nodes together, we would put them right next to each other. Clustering, proximity, the Gestalt principle of proximity, so that when I put these things together, I think of them as one group. Things that are tightly connected, so they're all connected to each other, I will group them together, put them off on the side. And we need programmatic ways of doing that. And that's actually a very big challenge. So we need to see what they're connected to, the paths that they're following. And so I don't want to overlap or cross lines. I want to figure out the network distance, how many hops it needs to take. So I want to put them sort of in some kind of line. That's these are the kinds of tasks I'm doing. I'm trying to figure out if this graph is connected. I'm trying to figure out the distance between this, let's say this node and this node here. 1, 2, 3. I want to see if I have a cluster. I want to see what kind of ordering I have. If I have a hierarchy, if I have subgroups, if I'm looking at people in a school and I want to see who's friends with whom and who's enemies and what the social groups in the school are, that's what a graph is used for. I lay it all out, who is friends with whom, and I see if I have clusters or groups of people. Who bridges? One of the things they look at for graphs and for social networks is who's a bridging unit, who's part of this group of people, who plays D&D on the side and then also plays football and also does this and also does that. Like who bridges multiple different groups. But sometimes not all attribute, it's not all topological based. So sometimes I want to know how many, if I have the grade point average for this group of people, or what the general grade point average is for everyone are. Sometimes I want just some statistics or attributes per node or per edge. We also briefly, I think at the very end, said, look, when we talk about graphs, we're talking about nominal data, and this is where texture, connectivity, and containment come in handy. So, and I'd also like to point out, this itself is what's called a bipartite graph, as in this is one group, this is one group, this is one group, and you can sort of make clean slices. These things don't actually connect to each other. They connect here to here, here to here. So what this one, and I'm doing containment by circling them, which is one thing we can do with our graphs. But a circle around things that are connected. This group of people in this class, circle them together. I might want to, if I'm showing the connectivity for COVID-19 cases in Ottawa, I can show a graph, and then I can circle. If I was doing it not on a map but on a graph, it would be, here are all the different COVID-19 places you could get testing. Circle the ones that are associated with Alta Vista. Circle the ones that are associated with this group. Circle the ones that are associated in this area. Lay them out, see which ones have some kind of connection between them. So we have a bunch of Gestalt principles, but the big ones are, we have grouping, as in I'll put them next to each other. Proximities, how close they are. I can group them, and I also have connectedness. That line itself tells me that these things are connected or related to each other. The node itself actually can be represented in a bunch of different ways. I can manipulate things. I could change the color of the node based off of hue, based on saturation, based on luminance, based on a lot of things, but a whole bunch of different ways I can encode that node via color. The size of the node, great. Also a way of encoding it. The shape of the node, they don't have to be circles. I could put stars and I could put triangles and I could do all these sorts of things. Very good for categorical data. Do I have another one? Oh, I'll go one further. The outside edge of the node does not have to be equal to the inside. So I can actually do the thickness of the outside edge compared to the inside. I can change have two different colors on the inside versus the outside. I can do all sorts of ways of manipulating that node to encode data. It's just, heck, I could make it into a bar chart if I wanted to. It could be a glyph that I'm connecting all these things up. It is just some dot that I can manipulate. It's our dots that we had before, but it could be other stuff as well. The edges themselves, you can manipulate the color. You can manipulate the line thickness of the edge. You can give it a style, dash line, fold line. You can even give it a shape or direction. Or you can have a directionality, but you can also have the shape or style for this thing as well. Not just the line itself, but how the arrowhead changes. There's a million ways. It's just a line, like we were talking about lines and how do we encode lines. The mark is the line. The channel, and then we have a whole bunch of different channels where encoding, uh, maybe we're encoding the weight or the distance on using the color channel. Well, we have a line, and that's all it is. And you can manipulate it the same way we did before. So that's the reason I wanted to bring this up. That's the reason I gave this particular link. I would like you to take a second and we're going to look at this. Here's a bunch of nodes. They just have random IDs, type A, B, and A and B, right? They're just, think of them as categories. You can call them like 2400 students and, or IMD students and net students or whatever you want it to be. It's just a type, a category. And each node has a particular ID. So they uniquely identify the nodes. So I have 5 nodes and I'm going to have a whole bunch of edges. Uh, so notice we have a source and a target, source and a sink, or whatever you want to describe it. So there is a directed edge from 1 to 2 with weight 1. So what I want you to do, here's your task. Draw a node link diagram. And I would love, ideally, for you to be very creative with this. Have fun with how you want to draw this thing. It could be crazy pants. In fact, the crazier the better. I normally say just make it whatever you want, but then people have given me some beautiful, node link diagrams with this. So this, I will say, is a directed, weighted graph, as in 1 goes to 2, 2 does not necessarily go to 1. Notice we don't have 2 to 1 anywhere. We have 2 to 3, 1 to 2, 1 to 3, 2 to 3, but we don't have 2 to 1. And there's a weight per edge. So draw a graph and then manipulate, play around with it. Try different colors on this thing. Try different shapes. Then after, when you're done, upload it to lecture 14. I'll give you about 5 minutes now. I'm going to try it myself actually, and we'll see how we go. All right. Let me mute myself and then try to put this in there. I'm also going to turn off the edit access afterwards, so just in case you want to know. Okay, I just cranked out 2 of them, so I think most of you should be able to have cranked out at least one. Pass it into networks and trees. We're gonna have a look at this in a second, and then we'll go from there, in case you're wondering. I'm gonna say you have 3 minutes to submit it. Let me know if you can't do it in that period of time, but there you go. We got one. Yay. Okay. Right. I'm going to see about how other people see if I can get other people's examples in a second, but I just like to point out, right, nicely done. To this, oh, you just put the B afterwards. So instead of categorize it, you could literally just put the A right in the name. I never even thought about that one. That's nice. I like it. So one of my approaches was to use, instead of A and B, I used a circle and a square for the A and B for the two different categories. And then I did shaded in versus not shaded in for A and B in the other one. But putting the name right in there, perfectly fine. Here's where I have a little bit of problem with it. Just letting you know. Sorry, I don't mean to put you on the spot, Kai, but just because this is us playing around with stuff. The only problem I have with this, nice, it's a good directed graph, by the way, very nicely done. But if you're using red, green, if you're using a rainbow color map, which is what this is, right? It's going from red to purple. What do we know about rainbow color maps? They don't encode continuous data very well. They're terrible. They're perfectly fine for categories, but people don't have that ordering in their head, right? To go from yellow to green, that people invert it oftentimes. It's not a natural mapping. Just letting you know, I will hold people for the final project at least accountable for that one. Rainbow color maps are not the way to go for normally for continuous data. And since we're assuming weights in a continuous data range, it's either this is this quantitative data. It's just the number system. And as a result, what you would get is you're not gonna. If I would actually go from like a like unsaturated red to a saturated red, which you can't really do with pens, obviously, right? Or you might go from uh, light blue, dark blue, or things like that. You could do that if you wanted to use color, right? Color worked well for like if you're continuous range, I'd be using like saturation or luminance as the big two for that. But nicely done. Let's see if I have another one. Let's click it again. Boom. All right. So let's pick on some people. Who do we have not normally pick on? We pick on everyone. You guys are the usual suspects. You're all doing great work, by the way. Madison, I don't get to pick on you that often. I don't think always. Sometimes, I guess. Nice thickness, beautiful. Completely different colors for the two different categories, right? Color works great for that. Different hues work wonderfully for categories of data. Uh, the line thickness clearly, because if you don't need to read the exact number off of it, thickness, it's clearly that this is a bigger connection between 1 and 3 than, let's say, 1 and 2. And these are relatively small connections. Oh, this 1 and 4 is a line width of 2, is it? Where it goes back and forth. Is it bidirectional? I'm not sure. I would have to look at the data again. Okay. I actually have a whole bunch of mine. Original one has a whole bunch of lines versus the thickness. And then it has the number right on top of it. The number right on top of it, not very, I mean, it's accurate. You can read it if you need to read the actual number, but it does not convey things the way that this thing does. This is clearly 1 and 3 is a big connection. It's 2 for the weight and for the weight and 7. Yeah, but depends on how you want to do things. But yes, you're right. And the thickness actually conveys it better, I think. So I just want to try something that I didn't think other people would give me. Nice. And this Sandy, you don't have your weights on it. You have categories on the side. That's fine. There's no weight encoding on this thing, right? So you're leaving some of the data behind, but that's fine. That already. Oh, nice. Oh, except for you're doing your encoding of different shapes based on each of the IDs. Now imagine you could also do your categories based on the shape. So 2 stars and circles, or pentagon and diamonds. This is where we were taught for the Working Women on the Go group. They had all these shapes for whether there was construction, whether there's a crosswalk. And I said, no, don't make them all diamonds. Make them a different shape so they pop, right? You want a perceptual pop so that you can actually, I'm looking for diamonds. You will spot that a mile away. If they're all diamonds, you won't be able to see it. You're not going to look at the individual icon. You want something that really, the color, you want shape, you want something that's going to easily allow you to categorize and define things or differentiate things. And I'm assuming you're using weight with different colors. You do the rainbow color map though. It's hard to do it with pencils, but next, what else we got here? Oh, wow. But is that the weight of the destination? Because you can't weight the inside part for the destination, right? I can't show the connection between here and here with 7 circles because it's on the line itself. But the weight, you can increase the size of your nodes to change different weights. So can you walk me through what the number of circles inside are? Yin? Oh, and there's your A and B using color. Beautiful. Oh, okay. So 1, 2, but this is 2 and 2 here. That's 3. That's number 3. Okay. So it's, if you were trying to show the ID number, then one of them, number 5, would have to have 5 circles inside of it. Still doable. We have a hard time counting, and especially for an ID, which you're going to count it and think it's you're going to think it's a magnitude rather than an ID. It's going to be slightly different, but that's really nice, and I love that color scheme. Let's do that. Nice, different. Oh, it's more than that's more nodes than we have actually, but it still works. So you fill it in. This is different team size, number shots. Oh, nice. So you did it for a data set, but it definitely counts. Still works for players shots on goal throughout the hockey season. Player and the goalie. Oh, interesting. It's all good, right? Another graph, also conveying information, important information. And notice that the goalies don't take shots at each other. I know, crazy. One time a goalie scored in the NHL, and that's because it was an empty netter. I remember the game actually. Oh, nice. Different colors for the outside, and then we have weights using a whole bunch of different color scales. Possible, but notice, if you take away that the color, your color map, do you know what the pink means? I think that's one of the things when we were looking at, I was looking at the outdoor activity groups icons, and I was saying, like, do the squint test. It's one of those things I used to do for HCI, the HCI class I used to teach. Do a squint test, just one of those things, right? Will you see what the icon means when you squint your eyes? That's sort of this little mini rule that we have. Can you differentiate them and figure out what this thing means if you squint your eyes? In this case, if I take away the the uh, the legend here, will I understand what's going on? If I take away the legend up here, I may not know A and B, but I definitely know they're different. And I think of them as categorically different. That's what I want, right? I want to, even if you don't know what that actually represents, you know they're categorically different. If I see different colors and I take away the legend, I think of these as categorically different than this, which is categorically different than these two. Because hue is seen as categorical, not continuous. And so this is the kind of thing that you play around with, right? Do a couple passes at this and see if other people misinterpret your work. If you take away the legend, do they understand what's going on? Oh, nice. We have directionality and we have the thickness of the line. Oh, that is beautiful. Uh, we have different color encoding. Notice I'm not sure how I want to interpret this, right? Because you have different, I would actually interpret this as a thickness from the outside to the inside as some kind of continuous measure that's being done. But it definitely, I mean, this is your A's, this is your group B. Your A's are also larger as well. You have multiple redundant encodings, which is not necessarily a bad thing at all. Although I would think of this as a stronger effect, unless these are the same size, in which case, if they're the same size, I don't think they are. If they were the same size, then we have a perceptual, we have a perceptual illusion because you're thick in the outside edge. It looks smaller than this, but I think this is actually larger. Nice. And notice how the encoding is done. It's using a triangle to indicate directionality. Nice. Love it. Different shapes, felt line thickness. Don't even need color at all. Clearly conveys information. Notice also what we have here. Choosing where you put your 5. You could put your 5 over here, and there's nothing wrong with that. That's in fact part of what we're looking at is you can choose your layout on top of just how you encode things. Choosing your layout, an optimal layout, avoids crossover effects, which is people tend to prefer. Is one of our heuristic measures is avoiding crossover lines to reduce confusion. So if you can avoid uh, flash, see if we have this one. Then I'm gonna so slow with PDFs. I'm sorry, that's not you guys. It's pure. Oh, that's already did that one. We didn't do Terra. Let's do this. Okay, so let me think here. A to B. We don't have the connection between 2 and 3. This is a tree. See what we have here? This is what a tree gives us. And you can't do a tree with, because we have to show this 2 and 3 connection. This is a great tree hierarchy. We're actually directly encoding the actual category on the side here, and the ID is just very explicit about this. And then we have, is this the number of edges or the width of these lines tells you something? No, because 1 and 2 has width 1. So can you walk me through this? What, like, why there's 2 lines on this one, but not only 1 line on this one? Or just misinterpretation? Okay, starts kind of using more energy. Okay. Yeah, but it's not we're trying to, we have a weight between our different groups, right? So 1 connects to 2 and has a weight of 1. I can't change that data. I can't change that value. It's 1. That's what the table said. Uh, and then 1 connects to this other group here. The B group has more weight because it's, yeah, but it's just the nodes themselves are different than the edges. There's no actual connection between, like, if something's on the edge, it doesn't say anything about what the nodes say. So no matter how fast your computer is, the network connection between the two computers makes all the difference, is the difference. That's the speed at which the packet is traveling across the network, not necessarily the computers on either end, if that makes sense. All right. What else do we have? Oh, and this has different colors. the layout, notice that they grouped the similar B's together in this particular case. We align thickness to indicate the number of connections. And notice the edge can be down here, right in the middle, instead of at the arrowhead. That's wonderful. Notice what benefits you get. If you put it at the arrowhead, it tells you around the node who's going in and who's going out. If you put it on the edge here, if you're looking at the edge, I want to see directionality when I'm looking at the edges. If I'm looking around the vertex, I want to put the arrowheads near the vertex, right? They're both right. They're just different. They give you different advantages. Okay, I think we've like looped around. Very nice, guys. I'm loving that. Let's do just easier. Aha. Okay, so let's get going on what other things we're doing today. I love this example because you can do all sorts of crazy things. In fact, you could do, I think we had people doing like different levels of squigglies to give you a line thickness or the number of squiggles you have on the line telling you the weight of the edge, for example. You can do all sorts of things with this. Some are better than others. This one I don't particularly love, but I think this is just something you could have generated, right? I have different colors for the dots. I have different thicknesses for the lines, and I'm not sure why we have different colors here. 2, 3, 3, 2. That just might be the weighting. Yeah, don't like it. I like yours more. This is something I got from the previous. I got it from some of these examples I got from previous instructors, and this is just one of those examples that they came up with, and I'm like, no, I don't like it. I like yours more. Nice. Previous instructors at Northeastern. We all sort of share things. So with the node link diagrams, what we want is they're distributed in space, connected to straight or curved lines. And what we try and do is avoid breaking apart that. So a typical approach is you put it in 2D space, and I want to break apart the breadth and the depth. So I don't really have any 3D depth to this thing. Um, and we're trying to show hierarchical information if we can. Fine. One of the benefits of a no-link diagram, there's other ways of showing a graph, by the way. This is what we're trying to point out here. Uh, People naturally get this one. You can show overall structure, you can show clusters, you can show paths. It's flexible. You can hold a whole bunch of variations. You can encode the nodes different ways. But my God, the algorithm for layout is really hard, and it's a lot of space. It's time consuming to run these algorithms to lay it out. We have non-deterministic results. That as in you lay it out again next time, it's going to look different. It's not consistent at all. Some heuristics for layouts give you just crappy results. And I love this term for really dense graphs, like everything's connected, everything. They call it a hairball problem. It looks like a hairball you pull from your drain. It's just this big clump of crap, right? You just can't see anything in this. You can't tease anything apart. When in fact, that's actually a common thing. Like everyone knows everyone else. You want to know that that's the case, but without looking like a hairball. Uh, so, and there's even more cons. The breadth grows exponentially. If it's a tree, it just goes like this. It just at the bottom of the tree, as you go down, every layer you go down, this thing gets wider and wider and wider. It uses up an incredible amount of space. So, and oftentimes I love the fact that we're choosing our layout. So the distance, you assume that the length of that line indicates something, indicates nothing. That's a big issue. You lay it out everywhere, and because you lay it out, you assume that that means something, and it doesn't. That's the challenge. So we can also pan and scroll. We can lay things out more. If we lay it out more accurately so that people understand it better, then you have to do a lot of panning and scrolling on your screen as well. You can't just sort of rearrange stuff. We need to do some filtering and zooming, and we can also do hyperbolic layouts, like as in shift things. Oh, wait, that is our focus plus context. All of those things that we were looking at before when talking about like showing the context and where you are, doing a fisheye lens on a graph, panning around, moving things around, zooming into your graph, all of that stuff, semantic and geospatial, I think, zooming, right? All our types of zooming, all of those things get applied to graphs. all directly applicable. So here's one of the things that you could do, and you can, this is something would never ask you to do because, oh my God, I can't do the algorithm. There are algorithms for how you lay out a graph. One of them is a spring layout algorithm. It's one of the more efficient ways of doing it. There's a bunch of different things you can do. The idea is, well, imagine if each node in your tree, we have a weight on the graph, and we have this spring connecting this node and this node. So if it has length 1, if there's no weighting, we don't even worry about that thing. But let's say we want to have the weights look correctly. We put a spring here, we put a spring here. We say how far apart how long that spring is. This is the metaphor, at least. Or you can do the spring with every spring being the exact same weight. Doesn't matter. So if I pull the springs apart, they want to go back together. If I push the springs in, they go back out. That's the idea, that they're always trying to get to that size. If I made it in the real world, that kind of spring, a bunch of springs connected together with hooked onto these little balls at the end, right? These nodes, what would happen? Well, some of them would pull apart, some would push in, but in the end, they all sort of get one shape. Now, it's stretched, it's twisted, it's, some springs are pulled more than they want to be, but at the same time, others are pushing in. We essentially get a stable layout at some point in time. That's the idea. If you put a bunch of springs together and pull them apart, did all this kind of stuff, and you put it down, it's going to form the sort of the orientation of minimal energy, the orientation that doesn't pull or push the springs more than that absolutely it needs to. We simulate that. So we say how far apart nodes are, and so we have some kind of vector pulling or pushing each one of these sets of nodes. And then we just say, try and minimize the amount of energy. So if it wants to go this way, it starts pulling this way, but then it's something else pushing the other way. And eventually you get to some stable state. And so we get things like this, and hopefully, I love just showing this example. So this is just me nerding out. This is a black hole. This is the algorithm in action while you're seeing it lay everything out. This around these nodes. Can I grab a node? I think it's still just moving. But we can change the spring coefficient. We can fix the spring length. There it is. It eventually forms some kind of stable state. I don't know why I'm still clicking onto it. Okay, there you go. But we can change the string length. We can change the gravity coefficient, how gravity works, all this stuff. And it just reruns the simulation and reforms some flattened version. This is just trying to find out different formats. This is what it's supposed to look like. And this is naturally what this thing will lay out to. It doesn't always lay out to the right format. This thing, it's still having trouble simulating, trying to get a flat planar surface, and it may not actually get to a flat planar surface. This is, I think it's just a sheet, rubber sheet, boom, fold back out this way. But this is what is actually happening for a lot of these layout for your graphs, is that if it's big enough, it'll do this. And oh, by the way, in case you're wondering, yeah, this is what will actually happen for a lot of your, if you're talking computer graphics, if you're trying to do mesh rendering, or if you have a complicated mesh and you're trying to deal with it, or you're trying to do some kind of distortion, they're running the same algorithm. It's the same thing. We just apply it in different ways. It's a node link diagram, even with the triangle mesh. Ooh. I think it eventually, it's a starburst. So these are floating out. This thing has a gravitational pull that's pulling everything back in. Oh, that's wild. That's what it's supposed to look like here. Anyways, I'm nerding out. So I'm going to flip back. But this is how we do a lot of our layout algorithms. We just do essentially a physics simulation to lay out our no-link diagram, and it'll get you what you want. And by the way, you have access to it. D3 actually does no-link diagrams. You can move this thing around, manipulate everything. Here's a no-link diagram in D3. Notice we have different thicknesses of edges. We have a graying of the edges to make it to mute so that we could show off the individual nodes. And we have different categories. I'm assuming, without looking at the legend, not knowing what the heck I'm looking at here, that's got to be categories. They're different hues. Okay. Here's another thing for Flickr query for the word mouse. And so we have different clusters. We have mouse as in mouse for a computer. We have mice as in the animal. We have Mickey Mouse. And then we have black, white, and mouse, all of the things that are in common between all of these network diagrams. This is what happens when you take network and you lay it out. You'll see clusters in your network. And then you can color by category by how this cluster works. Or here for that matter. This is tweets for the Windows 09 workshop. Who knows who, essentially. I love this example because Risk, the board game, you don't think of it as a network, but there's only so many places you can go. You can go from here to here. You can go from here to here. You can any adjacent country. But who cares what the shape of the country is? You just need to know what other country you can invade. Fine. This is actually what Risk looks like if you lay it out as a graph. And I'd like to point this out. So we have all these different things, like Ontario is highly connected, but it's only highly connected to other places in North America. South America's here. It's only connected, most of these are only connected to other places. North Africa has one connection to South America and a whole bunch of connections to Africa, although Western Europe might be a different category. They seem to be just one group. But Europe and, that's stupid, Europe and Africa is one place. Not, Africa's massive. Here's Asia, most of Asia, and here's essentially Oceania. Okay, I like to point out that this shows you or demonstrates one of history's greatest blunders, which is never get in a land war in Asia. The only other history greatest blunder is never get into a bet with a Sicilian when death is on the line. Ha 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 ha. Okay, so this is why that is prime real estate here. I'm going to move it back so you don't have to see Wallace Shawn keep falling over. This is why that particular place is high, like why Afghanistan traditionally, throughout the history of the world, is a prime target for all these world conquering nations where they're trying to, and they can never conquer it, but world conquering nations, because it's connected to so many other things. Turkey was that as well. It becomes this bottleneck where everybody needs, if you control Turkey, you control the world, essentially, at least at the time when they're rampaging across Asia or Europe, because it connects to so many other places. Okay. And you can even do this. When Donald Trump talks about things, what other related topics are connected? What other people is that person connected to? But here's one of the things I would like to point out before we're going to start looking at usability, I hope. If you're trying to do this on the local end of the machine, if you're trying to do it on the client side, right? I have a node link diagram and I'm trying to lay it out client side. It takes time. And you do not know what kind of machine the person has. They might be having a Chromebook, might be slow as hell. So one of the things you can do, just for future reference, is to to throw your data at some kind of server and technology like IBM Graph Layout. It's a it's a service that you can throw your data at. It will do the layout for you, and then it'll send the image back essentially to the client. So here is laying it out locally. Here is running the IBM, throwing the data at the IBM graph layout. Now, the data is already on the person's computer. So why would you need the IBM graph layout? Because it's still going to be faster. So here we go. 3, 2, 1, go. Done. Done. It's still going for all these things. I think we're going to do like double time. Finally done. It's very simple. Number 2 and 3 are still not done yet. Oh, there you go. And number 3, that's how big this data set is. Sometimes you want to put it on the server, get the server to do it. Okay. I'm going to skip ahead and jump to the usability testing right now. But I'd like to point out that notice this is a pretty crappy looking graph. There are better ways of representing some graphs, especially when you talk about really large numbers. So what we want to do, and when we next time we talk about graphs, what we're going to be talking about is some of the heuristics if we have time for more graphs, kind of ideal layouts and heuristics. If you are dealing with a graph, what's the best way of doing it? Well, first of all, you're going to try to avoid any kind of zigzagging. You're going to try and put things in a straight line if you can. You're going to try and avoid overlaps. That's the kinds of things. If we have central placement of high degree vertices, you put in the center and put everything around it. These are heuristic rules that people have discovered over the years for what people like to see when it comes to a graph and what's maximal for their ability to understand what's going on with the graph. So we have rules or we have heuristics that we put into our algorithms. So when we're doing this layout, how they weight or how they choose what the graph layout should look like is based off on these rules, such as if you have a layout, try and make it symmetrical, things like that. Okay, so let's bail on that. Let's jump over to this because I want to hit validation and verification. So let's also, this takes some time. That's why I want to make sure we cover it. Okay. The reason I want to go over this because I want you to think about how you want to test your system. Now, not the day that the usability testing is due. And ideally for an HCI, if we were doing it like an HCI class, I would actually spend multiple lectures just talking about how you evaluate this thing. We're only going to do a usability test. It's the bare minimum. It is the just get over the bar kind of testing. It is not, it's good for, is something terrible? Is it on fire? Is it going to, is it just a terrible experience for somebody? It is not the same as saying, does your system work? It's the same as, can they sort of do the task? You're not going to get empirical evidence. You're not going to get proof that your concept works, but it's better than nothing. I wish some people did use a bit more people did usability testing. So for an example for myself, I'm doing my taxes for this season. I want to look at how our retirement savings plans and pension plans work at Carleton. And so I'm looking around for how to log into various systems. One of them is the pension plan account, where you log into the system. It looks like 1990 something in terms of the layout. But not only that, but they hide what the person's trying to do is like 3 steps into the plan. It gives you this big long discussion about things, and then you have to click next. There's no other option for things. And there's on the tabs on the top, useful links is up on the top as one of the links. It's midway, not even at the end. It's midway through the set of links. If you click it, it automatically logs you out. Doesn't give you a warning, logs you out and just kicks you out of the system and shows you these other links. I'm trying to figure out how much money I should be putting into my pension plan if I want to put in supplemental money in the pension plan. And it's saying, how much money do you want? And it's framing the question in a way that is not what I want to know how much is coming off my paycheck maybe each time, not how much exact money I need in 2040 or whenever the heck I'm supposed to retire. It's not the task I'm trying to do. The task I'm trying to do is how much should I be putting away each and every month for my paycheck? That's what I want. And I want that front and center slapping me in the face. And this thing is like the most roundabout way of figuring out everything. And if you click the wrong thing, it boots you out. One usability test would have solved that problem. That's what we're looking for. When you pass your system to other people in this class and they go, I don't know what the hell you're trying to do, that'll be hopefully be the wake up call like, oh, I thought it was intuitive. It is not. It's everyone's going to have some usability problem, but your system, when you pass it to other people, they should know what you're doing with it. They're not going to read your instructions. By the way, this website that I was talking about gave an 8-page PDF describing how to do everything. And they have the gall at some point in time to say it's user-friendly because, which by the way, user-friendly means nothing. It's user-friendly because we give the definitions of all the terms. If you have to give me 8 pages of instructions on how to use it, you designed it wrong, period. So this is what I'm trying to avoid. That's what a usability test is for. It's for the sanity check to see if your system works. And that's what we're going to be looking at. Okay, so you're not going to be usability experts when you're done with this. This is a very, very small part of a very, very complex field. In fact, people just get their full PhD in just doing this kind of stuff. They will study their entire time, 5 years, studying how to evaluate some kind of system. I didn't do that, but there are people, that's what their study is, how to evaluate something. My master's and PhD both focused on testing, users and seeing how they do things. So I will ramble. I'll try not to, but I can talk for hours on this damn thing. I want you to have just enough experience at the end of this, just enough to realize what you don't know. So the Dunning-Kruger effect is a famous psychological experiment or a psychological phenomenon that people observe, where people are overconfident in what they know when they don't know something or where they have limited amounts of knowledge. So me playing pool is a classic example of Dunning-Kruger, right? You get there, how hard can it be? I'm just going to do this. I don't know how to play pool. I've played a bunch of times. I suck at it. But you don't realize how much you suck at it until you get more experience. You don't know how bad at programming you can be until you've programmed for a bunch. And then you look back and you go, oh, damn, I'm terrible at it. We want to get just enough for you to realize, holy cow, this is hard to do. That's what we're looking for. So, and normally at the start of term, and I will keep on poking you guys about this, it's hard to do. And I've been telling you, oh, that's not going to work. That's not going to work. Well, let's prove it or show it. If you can demonstrate that your system, if you ignore my advice and your system works wonderfully despite my suggestions, that's fantastic. I'm wrong. I'm okay with that. Most of the time, though, people sometimes I get students that will ignore my suggestions. They'll get to the usability test, and then every single person will hit that same problem, that same roadblock, and go, "That's the problem." And then the student goes, "Oh, okay. I guess he wasn't just full of crap." No, it's not my opinion. I back up with experience. So, like the squint test is one of those things that you'll notice the difference if you do it right, you'll notice a difference. You won't necessarily know before you make the change, but you'll notice a difference afterwards. Okay, so what are we talking about here? There's a bunch of different ways we can evaluate our system. In fact, we have a model about how to evaluate models. Okay. So that's what we're going to be looking at. We're going to be, at least the first part, we're going to look at the nested model. This is a Tamara Munster special. We're going to look at our previous iterations of this sort of nested model in another light. And then we're going to look at how we go about our design process based on the nested model. What we've been doing all term, the reason we have this project, I might change some aspects of this project so that everyone does sort of the same thing. But the whole point of this project is to hit every single step or almost every single step of the development process for visualization, to practically hit things. And so you see why we do things in a particular way. We don't just guess. We methodically plan, then implement, then test afterwards. And we're going to look at different types of evaluations, ideally at the end, but not today. And why we evaluate, why and how we evaluate. What's the point of an evaluation? And you might say, well, because it shows up. No, it's not going to prove anything, by the way. It's just going to hint, because you can't prove things. You can provide empirical evidence, but we're going to provide empirical evidence. We're going to try and validate what we're looking at. If you design something a particular way, you want to be able to demonstrate that your choice was the right choice, or at least a good choice. So we're going to compare to what default would be, maybe. So here is the nested model that we're talking about. Oh, actually, this is not the nested model quite yet. Most visualizations are bad. That's a bit of a bold claim, but we're getting better. But enough people just sort of off the cuff design something the first guess, right? Like what we did with the no link diagrams today. It's your first guess. You would never actually try and implement it based on your first guess, or you should never think to implement it off your first guess, right? You doodle something like what we did, like mine, wrong. After doing 7 lines, I'm like, oh, hell no, that doesn't work at all, right? I go to something else. You doodle, you plan, you critique yourself, you iterate a bunch of times. When you finally get something that you think is right, you run it by people again. Then you do some more work and you run it by people again, because otherwise it's going to be wrong. It's always bad and ineffective. That's why we need strategies, how to design well, and then proof. I don't want to say the word proof. I should have modified this. Evidence of effectiveness. You cannot prove anything. You're just providing empirical evidence. You're providing observations, statistics, whatever the case is, for why this thing seems to be working. So here's a nested model. We figure out the domain. Step 1. That was project 1. So for an example would be FAA aviation. So we're looking at the Federal Aviation Administration, I guess the FAA, who controls the airplanes in the United States. You figure out what they're trying to do. Then you figure out what their task is. So you got to know who they are. Then you figure out the task abstraction. Can I figure out what they need done? What is their task? What are they trying to do? That, by the way, is what your usability test is going to be dealing with. Project 2 looked at, here is, Project 2 was looking at, here is the task that we say, would you need to do? And I was being very, very mean about it, maybe. I don't know how you want to describe it. I was been very firm about tasks, and people probably go, why is he being such a jerk about it? Because it's a be all and end all. If you don't have the task, you don't have the system. You can't design for a moving target, or you shouldn't, right? So when you figure out the task, now you can design the right thing. And until you get that task, you don't know if you're designing for the right plan or for the right set of criteria. Once I have that, then I figure out my visual encoding. That's the first step you do. That's just the design step. I got 3 steps in. I'm 3 out of the 4 steps in, and I don't have any code written. In case you're wondering why I think code is the throwaway trivial part of this whole process, it's because it is. It's not trivial, actually trivial, but you're 3 steps in before you even touch code. Code is the last thing, or it's the thing that you don't concentrate on. You've got to figure out what their task is, who they are, and what kind of visual encoding you're going to do. And then and only then do you figure out how do you code it. You're not coding and then seeing where, you don't code and then figure out where it applies normally. So do you use a map? Do you use a scatter plot? Why? Justify each step. Then we do our algorithms. We do our code that actually is going to do something. We figure out if this approach that we're doing is more efficient. Those network diagrams, like the black hole visualization that I showed you, where everything lays out, that has a particular algorithm. Certain algorithms are slower than others. Certain algorithms are more accurate than others. You can analyze that. That's pure CS. That's pure programming, computer science stuff. That's where that's living. The rest of this stuff fits nicely into social sciences. It fits into computer science as well, but it's this hybrid multidisciplinary approach. As soon as you get in here, you're really into code, but that's 1 step, and then you're back out again. So we're going to analyze the computational complexity. We're going to figure out system memory, clock time, whatever the case is, the very programming CS stuff. But you guys, this is where you live. If you're anyone doing anything with users, if you're trying to figure out journalism to represent data for journalistic purposes, if you're trying to make a graphic user interface, if you're trying to make your user interface designer, that's your wheelhouse. You need to be able to speak this language down here, but they're not expecting you to necessarily code. You need to be able to code. You need to be able to understand how code works, but you need to also understand who they are, what their task is, and how to visually encode it. And you can do all that before even programming. So programming is important, but it's not the be all and end all. It's also not throwaway either. You need to be able to put on multiple hats. And it's not trivial. It's not your gut. I don't give two craps about your gut. Sorry, pardon for me for being blunt about this. Your gut is only the first step. You got to back it up with empirical evidence. So after my visual encoding, after making this, I want to analyze the results qualitatively, see someone use it and get some qualitative results, or maybe measure it in a controlled lab experiment, do a usability test, whatever the case is. This is me validating what I chose, my choices. Then I'm going to observe it in like a field study. I roll it out to a small group of people, see them use it. I want to see it in real use patterns. So I might, for the COVID testing group, I might roll it out to a subset of the population. I may have something to help COVID people find a COVID test, and then maybe I make a system that to a random subset of people of users, I show them the visualization. I show them the map visualization, and compare that group with the other group, right? The default standard, what you have right now, to your new system, and see which one gives you better results, right? It's a field set. I roll it out, but it's not fully deployed. Or I can measure adoption. So if I make something, will people actually use it? That we're nowhere near doing. It's very, very hard to do. If you make a system, will people use it? If you make a system that is supposed to be better than Excel, will people use it? If you are making a system for helping people find exercises to do around the Ottawa area, you can roll out the system, you can make it visibly available, you can advertise it in the newspaper. Do people actually use it in the end? That's what we're testing. That's a thing you can test. You can see the number of users. If it ramps up, goes down, how many people come back from multiple views, that sort of thing. But this is our nested model. And if you get any part of this wrong, it has consequences. So to understand the user, this is where human-centered design comes in. This is why we do what we do. Then we try and structure data. We look at our how we design our visualization, and we still haven't coded. I'm just doodling out my bar charts now, or whatever my visualization is now. But notice all the work I have to do to get here. This is a crazy amount of actual work, but it's dependent on the level above it. So if I do this part wrong, then I get the algorithm wrong. If I get the algorithm wrong, I waste a crazy amount of time. Implementation, and then I can do everything afterwards. I identify the problem, then I design things. So people think of visualization being in this area, but it's the whole stack. It's just some people have different specialties. So my specialty would be more the algorithm and the interaction idiom versus domain situation. Here's the weird thing about this. If you do it top down, notice what we have. Or we can also do it bottom up. So I don't know the order of my animations here. So if I do it top down, what do I get? I figure out the domain, then I figure out the task abstraction, then I figure out the idiom, then I figure out the algorithm. If I get the domain situation wrong, what happens? It's wrong, that goes to wrong, that goes to wrong, that goes to wrong. If I make a mistake at the start of my math proof, if I'm doing a math problem, let's say, not even a proof, just a math problem in high school, and I screw up at the very beginning, then the next step is wrong, then the next step is wrong, then the next step is wrong. That's why that's so hard to do. And that's why we put so much time in it. You got to get that first step right, or be very, very confident that that first step is correct. Have some evidence to back up your claims. Then the next step, make sure that that's right. If your idiom is wrong, you will waste a crazy amount of time building an algorithm or writing your code and finding out you have to throw all of it away and go back to the drawing board. That's why this is throwaway. It's not, but it takes up a lot of time. But it's dependent on all these previous steps. Errors propagate down. The bottom-up technique is a bit of a weird thing, and it's not as popular anymore. The idea is I may have a idea for how to do a layout for, let's say, a graph layout algorithm. I build my graph layout algorithm. and then I go and search for a domain where it gets applied. That is very much, computer scientists looking for a problem. That's fine in some cases, but it doesn't actually solve a real user's problem. It is, I have an algorithm, I'm going in search of a problem. It's normally for research. It's not for practical, real use. You don't build your algorithm and then figure out what, in a company, you're not going to build an algorithm and then figure out where it gets applied. You need to know what you're doing and then build your algorithm. For you guys, it is only going to be top down. You're trying to figure out how to present to regular, if you're doing data journalism, it's how to present to real people about a particular topic you're trying to teach them about, which requires you knowing what they know, what they're trying to do, what they're trying to get from that system, and building it, the sort of the idiom, how do you look at the data, and only then coding something. Versus a technique, right? One's a design study, a design go all the way down. The other one is just I build a technique and look for a problem domain. And that thing is one hell of a step. I'm not sure all of us have it right. I'm not sure I've ever gotten it 100% right, ever. It is, and people just take it for granted. Figuring out what the task is not trivial. In fact, one of my favorite papers, it's actually not one of my favorite papers, but there's a paper called Many Bills. There was a system a while ago called Many Eyes. It was very revolutionary. People were very excited about it. You probably never heard about it. So Many Eyes is made by IBM. The idea is it made visualizations that people could throw their data up online and they can make it's a crazy revolutionary idea. They can make a visualization on a website and then share that link. You see it everywhere now, but this is a site that started that trend. So it allows you to upload your data and share it with everyone else. That's what Many Eyes does. Very, very impactful system. Many Bills was meant to do the same thing, except they took all the data about politics, what the House of Commons does, not the House of Commons, American politicians do. So the Senate and the House, and all their bills, and what you can actually look at all the bills that they do in the U.S. government. And the idea was they were going to visualize it for average everyday people, and that people would suddenly become, well-informed and enlightened members of society. And then they looked at who was actually using it. So they built the system, had people use the system, rolled it out to the world, and who used the system? Beltway insiders, people that were political geeks and Beltway insiders, as in people that were in politics. They were weaponizing it to attack other politicians, but hardly any regular person looked at that site. It was designed for regular people wanting to look at how their politicians were doing or what bills were being passed. And the only people using it were politicians and people heavily involved in politics. It was helping them digest this really deep, heavy domain. Still useful, completely wrong task for what they're trying. That's what we're trying to get. I'm trying to make sure that you have the task right. So people were saying, well, I'm going to show this, I'm going to show that. I'm like, what's the task? I kept on, sort of harping on you guys on this one because you need to know the task before you can design it right. Okay, because mistakes propagate through the model. Okay, we also have threat stability. This is a fancy pants term for what goes wrong. So here are threats to validity. You got the wrong problem. If you observe the people wrong, you look at the wrong person, even, you're going to get the wrong solution. The classic example would be for the data dudes group, right? You have a classic problem of that. Not your problem. It's something we can't prove necessarily. I was nervous about because we do not have direct access. I could not put on. I sort of tried to fake, or I sort of talked about investments in Ottawa, but I'm not an investor, right? I'm not doing that full time as my job. And therefore, any conclusion you make from what I say might be wrong because you should be talking to a real investor to know what real people are doing. Because you could be, if you're observing or interviewing the wrong person, you're going to get the task wrong. Okay, or the domain wrong. The task, I need to figure out what my data abstraction is. I need to figure out what the task is, what people are trying to do. So I should be testing target users. I should collect anecdotal evidence whether something is working in order to validate my system. So, or if I get the problem wrong, adoption rates won't be right. That's how you validate whether you're going to get the right thing after the fact, of course. You can validate before, you can try and validate afterwards. The problem is the task is wrong. I can try and check with my users to see if it's right. I can test people using the system afterwards to see if they use the system the way I expected them to. I can do field studies. I can do human, I can try and deploy the system to a subset of users. I can do A/B testing. Here is our visual encoding. If I have the wrong visual encoding, I use pie charts. Boo, pie charts. If I use rainbow color maps for continuous data, whatever the case is, I can, to validate it initially before I design anything, what I should do is step by step go, I'm doing this. Is it justified based on the theories, based off of what research we know, based on heuristics or rules that we have for design? Is it right? That's what I'm asking you to do for your assignments, especially for your final. I did this because of this. I did this because of this. I'm using this mark, these channels. I'm using shape because it's attentive or gives a pop out effect. I am using luminance because it's good for encoding continuous data, right? Justifying why you design something a particular way. And then after the fact, this is where we're going to go. You do a user study. You do some kind of qualitative test. So you talk to people, interview people, or you do quantitative, you bring them into a lab, you do usability tests, right? You're trying to test error rates. That's how you validate your system actually works. Can they do the task with the system correctly? That's only after you've built the system. So the first step, the thing that saves you easily each time, is some kind of validation as you go. And notice, task domain doesn't have an easy validation. That's what's scary about it. The other ones you can validate before you try and implement. And then finally, for the algorithm, you can measure it. If you have a slow algorithm, you can calculate the computational complexity of your algorithm before you code something. You're not going to do that in this degree program, but computer scientists do this. They figure out the big O complexity. It's the speed in which the algorithm approximately goes. So you use binary search instead of linear search, for example. You use a quick sort algorithm versus bucket sort. Then you implement your system, and then you actually measure it. You use clock speed. You actually calculate how much resources are being used, that sort of thing. Okay, for your final project, this is what you end up getting. You validated in project one. You observe and interview your target users. You figure out what your task is. Great. You justify your encodings. When you're designing your thing for P4, that's what I was expecting. We did this for this reason. We did this for this reason. We did this for this reason. Validating based off of what we did on the lectures. Go back through the lectures and see what fits based on based on what you're doing. And then afterwards, this is P7 right down here. We're going to evaluate how the system is being used. And we're not even touching this. This is future work that all of you are going to have in your final project. So for your final project, you'll have a section that says future work, and you'll talk about all the glorious things you're going to do with your system afterwards. And I know damn well you're not going to touch this again. And you know damn well you're not going to touch this again. And that's fine. Don't go too crazy and say, oh, we're going to do this and we're going to do this and we're going to do it as a summer project. Don't completely lie. We know you're not going to touch it again. But what would you do if you wanted to evaluate this further? What would the future steps be if you continued? Would you roll out to the average person in Ottawa? Probably not yet. Would you test it off of real people using your system for a week and then roll it out to the average person in Ottawa, give it to the city of Ottawa to see if they can use it? That seems reasonable, right? How would you go about evaluating the rest of your system? Okay. I'm gonna. Oh, I'm over time. So let's just hit 3 things that we're going to pick up next time. There are 3 ways we can look at models. We can look at software, a UML diagram, like a UML diagram. This is how the code looks, the program looks. We can look at how our design decisions work. So this, the nested model, how we decide the model for how we go about designing systems. And then we have the process model, this sort of thing, how the design process works, how it lays out, how you, what phase you're in the design process. And that's where we're going to pick things up next time, where we're going to look at usability testing, and we're going to talk about what kind of usability test you want to do for your system and how it's going to look. And we'll talk about what P7 is going to be. Okay. I'm going to be, it's office hours next, so I'm just going to be around. Just ring me up if you want to chat with about your project or what, you know, one of your homeworks or whatever the case is. Okay, thanks everyone, and I will stop right now, and I'll talk to you soonish. Thanks.